All right, this video is going to talk about Gaussian elimination, but first, in order to talk about Gaussian elimination, we want to think about what kind of answers could we end up with when we're solving a system of equations. And when we're solving a system with three planes or three variables, when we talk about systems that have three variables, such as the one we have on the next screen here, notice we've got three equations, but we're dealing with both x, y, and z, right? We're dealing with all three of those. What really we're doing is, in three dimensions, when you graph an equation, what you're really doing is graphing, right? Three planes. You're not graphing a line anymore, you're graphing three planes. So typically what we like to have happen in a consistent independent system is those three planes intersect, kind of like in this picture in the upper left, in one dot right in the middle. We get one simple, consistent, independent answer. Now, occasionally we might graph these, and again, maybe they'll never cross, right? They could be inconsistent. Maybe the three planes don't cross at all, such as down here at the bottom, right, down on the lower right. We would call that an inconsistent system, and that's fairly simple. When we're solving that system, it comes out pretty normal. Usually we'll end up with, we'll eliminate our variables, and at some point, we usually end up with something like 0 equals 1, or some other impossible statement. So a lot of times that sort of thing will happen. That can also happen to you over here on the left. You can also be inconsistent if maybe the planes come together, but all three of them never come together in one place, right? What if we have this situation where, again, these two came together in a line, these two in a line, those two in a line? Well, in that case, again, it's inconsistent. There's no one solution, right, that would be on all three planes. There's no one spot that kind of runs into all three. The one we want to be careful about, and it kind of has a simple way of writing down the final answer, is what if we have multiple answers? And this is just one depiction up here of what that could do. If we have three planes and they all come together, kind of like the binding of a book, right, where all the pages come together in one place. Well, all of the points on this line are on all three planes. So again, we call that a dependent situation, right? It's dependent because there's lots of answers. And if you want to identify one of them, it depends upon you naming a variable so that we can identify which point of all those points that you want. Let's take a look at a couple examples of dependent systems, and I'll show you how you can write those out. All right? Now, I know ahead of time this one's going to be dependent, so just be pre-warned. Normally, I would just be solving this equation, kind of going my merry way, and we wouldn't worry too much about that. Now notice right away we've got a nice system here because we already have that 1x in the upper left corner. So I like that equation staying where it is. I'm going to leave a up here in that upper left corner. I also actually have a really good equation b right now. There's no x, but we have 1y. So we're actually in really good shape as far as that goes as well. However, lastly, we want to get rid of that x down here in equation c. We also want to get rid of this y. We want to end up with just one z, right? If we want to be in row echelon form, we're going to use Gaussian elimination here. So if we wanted to have that sort of stair step, x, y, z, we need to sort of introduce a z but get rid of this other stuff. So let's go ahead and start off by just saying, well, let's just add equation a to equation c, because x plus negative x will disappear. This will become a 3y. Again, we get 3z plus 0 is just negative 3z here. And we get negative 1 plus 1 would be 0. I'm going to call that equation D, and I'm going to keep on going here. So again, we're going to keep equation 1. We still like it, right? I still like that top equation. I'm going to keep the second equation. I still like that one. It's in really good shape. But now I need to get rid of that 3. So why don't we go ahead and take, again, A is here, B is here. Why don't we go ahead and take equation D, and let's subtract 3 of equation b, right? So let's just do that up top real quick. 3y minus 3z equals 0. I'm going to multiply the middle equation, negative 3 times the y value. Negative 3 times 1z is going to be a positive 3z here. And negative 3 times 0 is still 0. We'll add those up, and notice, dependent system. Again, that's all my variables disappeared. But at the same time, right, at the same time, it's not a false statement. We got 0 equals 0, which just tells us, again, there's infinite answers. There's going to be many answers to this. It's a dependent system. Well, we could just say there's infinitely many solutions, but we'd kind of like to narrow that down. It's not that we can plug whatever we want into our equation, right? You can imagine down here with equation B, if I got to take y minus z, well, I can't just plug whatever I want in there and still keep that a true statement, right? 5 minus 4 isn't going to be 0. But what we want to do is be able to represent quickly and simply, without having to write that whole system out, an easy way to represent those answers, right? So that we can write them all down, or at least show how to represent all of them all at the same time. We're going to use a little bit of substitution. So what I'm going to do is I'm going to go ahead and use a to my advantage. I'm going to use the lowercase a to my advantage. What I'm going to do right away is I'm going to say z equals a. And I'm going to put everything in terms of a. We're going to put everything in terms, right, of a here. Well, if z equals a, we've got z handled. What I'm going to do is go back to my second equation then, my equation b, right? And I'm going to say y minus, but instead of z, let's plug in a, right? Let's plug in that a value. And now, what I want to do is solve for y. I like it up here where I've got z all by itself, right? I'm solved for z. I have a way to represent z. What I'd like to do is have y all by itself. So in that case, I'm going to add a to the other side. Just so happens that y also equals a right now. All right? Y also equals a over here. Then let's go back. Well, we've got y in terms of a. We've got z in terms of a. Let's go back to our original equation. We've got x plus y, but again, I know that y equals a, minus 3z, but again, I know that z equals a, is equal to negative 1. Well, that means that x minus 2a equals negative 1. And if I add that 2a to the other side, x here, equals positive 2a minus 1. I'm just adding 2a to the right side there. Well, now we've got x, y, and z all in terms of, right, that variable a. So if I want to represent the system, what I can do is I can say, well, this is really the coordinate point, 2a minus 1, comma, a, comma, a, right? Z equaled a, y equaled a, and x equals 2a minus 1. So now if I want to represent a few different coordinate point answers, all I have to do is pick an a value, such as, say, 0, and I could find a coordinate that will definitely solve my system. If I plug 0 in for a, well, 0 times 2 is 0, minus 1 is negative 1. And again, a is just whatever I named. So I guarantee you the point, negative 1, 0, 0, would be a good solution to my system. I could also pick a number like 10, right? 20 minus 1 would be 19. 10, 10. And I'll tell you that 19, 10, 10 is also a solution to my system. I can pick whatever a value I want, and I will now guarantee you that we'll get an answer or a solution to that system. Let's take a look what happens when we don't have enough equations. Remember that you need as many equations as you do variables, or as you have variables, in order to guarantee yourself, or at least have a chance at even, getting a consistent solution that's independent to get a single answer. And you can kind of think of that RREF idea. You would do that stair step, right? We could make that stair step idea. Well, right now, if we try to get rid of x, I'm not going to be able to have an equation with just z in it because I don't have another equation. So there's no way I can narrow down to one variable. That just tells me right away I'm already going to be a dependent system. So the first thing I would do, again, I would really still want to try to get rid of x. So I'm going to go ahead and take row 2 minus 2 of row 1, and notice here's what I get over here at the right. Okay. Now, since I'd kind of like that to be a 1y, I'm also going to divide that equation by 3, just dividing by 3 there. So now I've got y minus z equals negative 1, and now we're ready, like we did on the previous screen, to do a little substituting. Z, right, is going to equal, well, I'm going to subtract y over to the other side. And then I can, and that's negative z, right? If I subtract the y, it's still a negative z. Well, I'm going to go ahead and run a negative through there then. Z equals positive y, right, plus 1. Okay. Well, remember, if I took out z and I called it a, right, that means that right now Oops, we did that wrong here. Just a second. Let's write this down as we go. Z equals A. Let's do that first so I don't mess up here. Then Y minus A equals -1. I'm going to add A to the other side. There we go. Solve for Y. And then let's go back to our original equation. X minus 2 times Y, right, which is A minus 1, plus Z, which is A, equals 2. Sorry, I kind of mushed that into my other equations there, so I'll move over a little bit. Do a little distributing. I'm going to subtract my 2 over to the other side, but I've still got X minus 1A here, and it just so happens on this one that X ends up equal to A. So again, the solution to my system then, right, or my easy way of writing this in terms of A, well, X equals A, Y equals A minus 1, and Z equal to A. So that, again, if I wanted to go find 3 solutions to the system, what I would do is just make a simple table and pick 3 simple numbers. How about we just say -1, 0, and 1? How's that sound? That means that A equaled -1. -1 minus 1 would have been -2, and another -1, and we've got a solution to our system. If A were 0, that's 0, -1, 0. If A were 1, that's 1, 0, 1. Again, you can plug whatever number you want in for A, but again, you can't have a unique solution, right, a single solution, unless you have as many equations as you do variables. Right now we have a dependent system. We get answers, but it depends upon, right, the answers depend upon us choosing an A value in order to identify an individual answer. I hope that helps you with solving systems with Gaussian elimination, as well as how to deal with dependent systems. Make sure you talk to your teacher if you have any questions, and have a great day.